Hello, everyone. Welcome to another episode of Q&A about future of science and technology. Let me see a few questions here. There's one from KD. Many fusion energy startups have appeared in the last few years. What scientific and technical challenges need to be resolved before we see commercial applications? Well, fusion is one of those funny technology stories where people have been trying it for 70 years and it hasn't worked. And presumably one day it will work. But there's been kind of 70 years of attempts that haven't worked. So let's just define what we're talking about. So fusion is the same kind of source of energy that powers the sun. And it happens when you take light elements like hydrogen, and you can, if you take hydrogen nuclei, protons, and you try and kind of make them collide, it's hard to get them to collide because they both have positive charge, and there's an electrical repulsion force, and you have to overcome that electrical repulsion force somehow. And the most obvious way to overcome that electrical repulsion force is the way it happens in the sun, which is the protons are just going so fast that they kind of get over the potential barrier of electrical repulsion and manage to interact with each other and can undergo fusion. And it just turns out to be a feature of nuclear physics that if you take light nuclei and fuse them together, the resulting nucleus has more binding than the energy than the individual previous nuclei, and so energy is released by fusing together light nuclei. It kind of goes that way until you get to iron 56 specifically in the table of isotopes. And as you go towards iron, it is the case that putting together light nuclei releases energy as they fuse. When you go beyond that, as you go to elements like uranium and plutonium, in those cases, taking the elements apart gives you energy. So for uranium, for example, uranium-235 undergoes spontaneous fission, and the nucleus of uranium-235 just falls apart. On average, it takes a couple of billion years for that to happen, but it will just fall apart and it releases energy when it falls apart. So that's the fission process that's used in current nuclear reactors and so on. It comes from the energy associated with what you get by breaking a big nucleus apart. But the fusion idea, which is what the sun uses to get energy, is to fuse together light nuclei. And the most obvious way to do that is to have something at a very high temperature, like 10 million degrees. And at that temperature, so temperature determines the kinetic energy. The temperature basically is the kinetic energy of particles. That's what defines temperature. And that means that the particles are going fast enough, have enough energy that at that temperature of 10 million degrees, let's say, that they can overcome the potential barrier and fuse together. And when they fuse, energy is released. So that's the idea. So now the question is, well, how do you actually make that happen? And there are several approaches. The most common approach is to just take something like hydrogen and make it very, very hot, make it 10 million degrees. Well, the thing is, at that temperature, you have a plasma because you've stripped off all the electrons from atoms long past doing that. And so you've got this plasma of, let's say, hydrogen or deuterium, or whatever, nuclei, and they're 10 million degrees in temperature. They're going around very quickly. If they were to collide, there's a good chance that they would undergo fusion. Well, the problem is, how do you confine a plasma at 10 million degrees? Well, it's not so easy because there's no material above about 5,000 degrees, everything has melted, everything is vaporized. You can't use a material object to confine a plasma. So, however, there's the convenient feature that the elements of a plasma are electrically charged. The nuclei are with positive charge. And that means you can use magnetic forces to confine the plasma. And so there's this whole idea of plasma confinement fusion. where you have a magnetic bottle effectively to confine the plasma. Okay, so that was the idea back in the 1950s. And at that time, I remember when I was a kid in the 1960s, people said it's going to work real soon now. Well, why didn't it work? You can make a magnetic field that will constrain this plasma. So you're heating the plasma up, you're constraining it, you're keeping it, confined, and then protons are going to collide and they're going to fuse and they're going to make energy. Well, what didn't work is that there turned out to be all these weird instabilities in plasmas. If you get like a tokamak as a standard kind of confinement configuration, it's essentially a torus, and you've got these particles going around in sort of an orbit in this torus, and it turns out there are these weird instabilities where when a particle has gone in one place on one orbit of the torus, it goes more further out on the next orbit and so on. And the question is, can you make a magnetic field that will somehow get rid of the instabilities? And that's what people have been trying to do for 70 years now. Now there's decent understanding of how to do that. Simulations have gotten good enough. The control systems have gotten good enough so that you can, when you kind of see a piece of plasma that's going out in this direction, you can change the magnetic field fast enough to be able to sort of fix that splitting out of the plasma and so on. So there's reasonably good reason to believe that you can successfully confine plasmas now. So one strategy is this plasma confinement fusion. There are sort of two famous configurations. One is this toroidal thing, the tokamak. The other is a thing called the stellarator. And it has, I guess it's called the stellarator because it's supposed to remind one of stars and how they work inside. The stellarators can be very weird shapes because they're set up to have sort of orbits that are all of different lengths. And so it's a very sort of asymmetrical, weird-looking object. But these are things, I don't know, 10 meters across of this order that maybe a bit bigger than that are trying to do this plasma confinement fusion. The biggest operation is this one called ITER, which is in the south of France. It's a big international collaboration that's been going for a disappointing number of years, and where, like any organization that gets so big and so many different sort of international pieces, it's hard to know whether it will ever converge. But in any case, the idea is confine the plasma, and now there are a whole bunch of companies that are going in this path with different kinds of tokamaks, stellarators, other such things. Okay, so will this work? Probably the confinement part of it will work. What I gather is that one of the problems is, in the event of success, things might go haywire. So what does that mean? Well, if there's success, it means there is fusion happening. When there's fusion happening, there's a lot of energy being produced. That energy has all kinds of consequences. For example, it'll throw out one of the things that will happen with fusion is you generate a bunch of neutrons. The neutrons, being neutral particles, are not confined by the magnetic field. They'll just zoom out. And whatever is producing that magnetic field, it's a bunch of magnets. And those magnets can be made, maybe superconductors, whatever, but they're materials. They're actual materials like metals and so on that are doing that. Well, if you successfully generate fusion, and that generates a huge number of neutrons, high energy neutrons, those high energy neutrons will hit all those magnets that you were using to make the magnetic field, and they can essentially shred the magnets. And so if you get successful fusion, one of the things that happens is you'll get all these particles produced. So that's a potential problem. It's not clear how that can be dealt with. Then you've got to actually take the energy out of the system, where you're going to heat things up. And then you've got to take that heat and essentially run it through, just like a steam engine at that point, what you're doing with that heat. That might not be problematic depending on how much heat is produced and how quickly and so on. So one of the issues is, if you've got a bunch of metal magnets, they might get sort of shredded by these neutrons and so on. They might get, their crystal structure might be destroyed, and they might kind of just essentially disintegrate. So what can you do about that? Well, one thing you could do about that is have them be made of liquids. liquid metal, for example, have have this whole sort of assembly be something that isn't something where, oh, it's destroying the crystal structure of this magnet, but rather these neutrons are crashing into something which is liquid, and then the liquid is just being recycled elsewhere. It's tough to do that in a gravitational field. Maybe not impossible, but it's tough to do it because you've got to get it in all directions. It's not like you can just spin it around and have it be just sort of, you've got one sort of centrifugal thing happening. So, I mean, the one thing I certainly thought of is, maybe you get to do this in microgravity in space. Maybe you get to have kind of the liquid there where it will just sit there. If you don't do anything with it, it will just sit there. It'll get shredded by neutrons, but then you just recycle the liquid and all's good. But that's a pretty high wire act to make all that technology work. But anyway, so that's the confinement fusion approach, plasma confinement fusion. Another approach is laser pellet fusion, where the idea and the biggest operation of this kind is in California, National Ignition Facility, I guess it's called. The idea there is you have this little pellet made of usually, I think, deuterium and tritium, isotopes of hydrogen, and coated with some mysterious collection of other heavier elements, which I suspect are still quite secret. The idea is that you have a large number of lasers that kind of suddenly fire, and the electromagnetic energy is all sort of crushed into this little pellet in the middle, and it is and that sort of all that energy causes the pellet to be compressed to the point where the deuterium and tritium inside the pellet get pushed together with such force that they can overcome this potential barrier and undergo fusion. And that's another approach where you're kind of charging up these capacitors to run a bunch of lasers. You run the lasers for some, I don't know how long it is, maybe hundreds of nanoseconds, I'm not sure, but very short amounts of time to generate this pulse, electromagnetic pulse that compresses this pellet and causes fusion. The issue with compressing something like that, same issue as in nuclear weapons actually, is if you squash things, they have a terrible habit. If you squash it one way, it'll split out the other way. And so it's a tricky thing. And when you see the pictures of like this sphere that is this laser fusion machine, it's just got a very large number of lasers, and kind of the idea is you're shooting from all sides so that you just get compression. You don't get something sort of splitting out on one side or another. So those are a couple of the approaches. Another thing that is sort of came on the scene, I don't know what it was in the early 90s, is cold fusion. The possibility that there might be a way to get fusion to happen without all of this heat, without all of this, heating up a plasma to 10 million degrees or having all these lasers and so on. And the thing that was done at that time was an electrochemistry experiment done in which hydrogen was essentially dissolved in palladium. Palladium is an element that has, I'm remembering that correctly. It was palladium. It has the interesting feature that the crystal structure of palladium is such that a huge number of hydrogen atoms sort of fit in the interstices of the crystal. So in fact, you can dissolve a huge amount of hydrogen in a piece of palladium. Well, what that kind of might tell you is there's then going to be a very high density of these hydrogen ions in there. And maybe there's a chance that with that sort of high density of these things, that somehow they'll be shielded from each other enough electrically by other pieces of the crystal lattice that they'll be able to get near each other enough that you can actually get fusion to happen, even without all of this ram them together with incredible energy. So that was an idea. In the sort of original moment, the sort of original experiments sort of quickly got discredited, but there kept on being kind of these reports of, well, somebody's managed to reproduce it, this has happened, that's happened. My own prejudice would be it's not obvious that it's not true. In other words, that it's not obvious that there's no way to do cold fusion, so to speak. There's a question of what happens in these experiments is, yes, there were some that were difficult to reproduce, but we don't really know what was important to the experiment. Maybe some detail of the atmospheric pressure, maybe some thing about the particular way that the palladium electrodes have been created. Something that we don't yet know what's important because we don't really know how the thing works in the first place will turn out to be important. Now, it's also worth saying that to get a little bit of fusion to happen is quite easy. You can do that, there are science fair projects that get a little tiny bit of fusion to happen by having by just accelerating particles and ramming them into something. You can get tiny amounts of fusion to happen. But the problem is, can you get enough fusion to happen that you're actually generating that the energy you spend accelerating particles to hit your target to get a little bit of fusion to happen, that energy is less than the energy you get out from the actual process of fusion. And that's really that's the break-even point that people say, well, this system will reach break-even in this year, and this one will be 10 years out or whatever. I don't tend to believe it when it's 10 years out, because much can go wrong from here to there. But that's kind of the idea. And I think it is a complicated story right now because, yes, there are a bunch of companies that are trying to do this. A fair amount of investment money has been put into it. I think that there will be tremendous enthusiasm if break-even is reached. Whether that will be enough to have power generation because of these issues about sort of what happens to the crystal structure of the container or whatever else is quite unclear. I think that there's sort of a trade-off here because the sun is a great big fusion reactor, sending lots of energy in our direction. It's difficult to harness that energy because photovoltaics are not that efficient, and a lot of the energy that comes from the sun, even if you have photocells collecting it, is most of the energy is not actually being converted to electricity. I think there are all sorts of things one could imagine that are sort of exotic ways to capture the energy from the sun in space and beaming it down to Earth and all kinds of things like this. It's not clear to me which of these things is going to be a winner, and it's not clear, if fusion energy worked and it suddenly became possible to make fusion reactors, then the fuel is ultra cheap. It's just hydrogen from water or something. There's no issue with that. It's even with nuclear reactors, current nuclear reactors, fission reactors, there still can be lots of they're fairly big uranium deposits. You don't need that much uranium to make a lot of energy, or that much thorium or whatever else to make a lot of energy. That's really because it's sort of an E equals MC squared story. You are converting mass into energy, and there's you don't need a lot of mass to make a lot of energy, so to speak, as opposed to what happens in a fossil fuel, for example, where you're converting the chemical bonds into energy. And chemical bonds are things that are in terms of sort of the physics orders of magnitude, they're in the electron volt type range. That's the typical energies, whereas the energies, nuclear binding energies and things like this are in the million electron volt type range. So there's a sort of a big difference between energy that you get from chemical bonds in a material like a hydrocarbon or something like this, where sort of it's sort of energy came from the plants that got it from the sun that did photosynthesis, and they sort of were storing their energy in this form of these molecules that had sort of bonds that had the feature that if you rearrange them, then energy is released. But that's of order electron volt type energies, as opposed to million electron volt type energies in the case of things like nuclei. So that's kind of why it makes sense to go for nuclear kinds of things. And in the case of fusion, it has the good feature that that sort of the fuel is infinitely abundant. Let's see. Des is asking a question. Why is it better to have tritium and deuterium in the middle of a pellet for for a laser fusion. I used to know the answer to that. I'm not sure I know immediately. As I recall, in a bunch of nuclear weapons applications, one ends up using lithium deuteride, not even, but I don't remember immediately why. So sorry, I don't know. Let's see. Gosh, seeing a bunch of questions here. HX asks, can you talk about LLMs externalizing their thoughts in chain of thought and how they could recompile what they learned into their internal multiway representation? Gosh. Well, so let's talk about LLMs. Let's talk about chain of thought. So an LLM, large language model, its goal is, its fundamental operation is, it's given a prompt, it's given a piece of text, it's asked to try and continue that text in a way that is sort of statistically appropriate given the trillion words it saw from the web and other places. So it's been trained on those trillion words. It's like continue from the input that was given, the prompt that was given, sort of just keep going as best you can. But the way an LLM works is it's always only looking backwards. It says, given what I've seen so far, what should the next word be? That's the typical operation of an LLM. And so what one observed from very early on is that an LLM would just keep splurting out various things, and you would say to the LLM, that seems to be wrong. And the LLM would say, oh, I'm terribly sorry. Yes, I got it wrong. Here's what's right. Well, what was it doing when it did that? Well, the answer is that when you said, now look at what you had produced before, you produced a bunch of stuff, now look at it. It then took all that stuff it had produced so far, that became its context. And it then was using everything it did before and trying to figure out what to say next. And at that point, it could see that what it had done before wasn't right. And so it says, I'm terribly sorry, I got it wrong type thing. So people then had the idea, this is probably 18 months ago now, of saying, well, let's do some kind of chain of thought. Let's say, let's lead the LLM through, oh, it does this first thing, and then it it gets to that point, it looks back at what it did, it keeps going, and potentially it, in some cases, then you can imagine a whole graph of possibilities. Oh, it did this thing, that was wrong, let's roll that back, let's try again, let's make a different kind of branch of sort of the behavior of the LLM. And that's a bunch of what these kinds of reasoning models and so on do. The LLM can grind away for half an hour, sort of getting to results, going back, looking at what it did, assessing that. You can do things where you have multiple assessors of a particular thing. So you can say, well, look at it in three different LLMs or three different ways that an LLM looks at it. Then you say, did they all agree that this was good? Then keep going, otherwise retry, and so on. I don't know how well this is all going to work. I mean, there are some impressive demos. I was just using this a couple of days ago, and it did really badly. It was, it was trying to do wonderful math, and it produced something that looked very plausible. It looked like a math paper. The only problem was it got the wrong answer. And then it even went and made up references, including even some to my own work that looked very convincing. They were convincing enough. I looked at that page number and oops, what it said was there wasn't in fact there. So that's I think, yeah, I think that's kind of a thought about that. I think the question here was about externalizing chains of thought and kind of feeding back. I mean, in a sense, a chain of thought does feed back in a one-shot kind of way what the LLM had produced back into the context for the LLM to go forwards. this whole question about feeding what an LLM produces back to an LLM to train the LLM further, in roughly, LLMs have sort of three levels of how they get told what to do. One level is their original training, where you're taking those trillion words or whatever, and you're trying to get a neural net to do the right statistical things. Another is so-called fine-tuning, where you're kind of you've mostly got the LLM settled. It's mostly got all its neural net weights settled, but you say, I'm going to have this little piece that I'm going to sort of try to add on to that to get the LLM to just be a little bit more oriented in this direction rather than that general direction. And the third is the actual sort of one-shot thing of here's a context, here's a prompt effectively, do things based on that. I have to say, I think that it is a tricky business. The whole training business is a very tricky business. It's kind of like it's kind of a whole art of how many times do you kind of, when you're going through your training data, how many times do you use each piece of data? Is it about once, or is it a few tens of times? Do you try and weight it with, data you think is more important or not? Does fine-tuning really work at all? It's not clear that it does. I did sort of left out the reinforcement learning step, where you're kind of having the thing try and produce results, and then you're feeding that back, the assessment of those results back into the training. And there's undoubtedly more innovation to be done, and there has been some quite recently on how all these different sort of levels of training work. It kind of reminds one a little bit of the memory hierarchy of computers, that computers can have sort of slow memory that is accessed rarely but has lots of stuff in it, and then faster memory that's accessed more quickly. It's the same as with us humans. We have a short-term memory that lets us kind of finish the sentence, so to speak, and that's very different from the long-term memory that probably has to get formed over the course of a day or something like this. That is what allows us to remember things long-term. Let's see. Gosh, let me see here. Well, interesting questions. Well, Akbar asks, do you think we will eventually find correspondence for all or most mathematical structures in the physical realm? That's a question actually that gets kind of philosophically complicated. But one of the things that's sometimes said is, isn't it amazing how successful mathematics has been in the natural sciences? Isn't it amazing that mathematical ideas that have arisen have turned out to be so applicable in the natural sciences? Eugene Wigner, physicist from the mid-20th century, was big on the unreasonable effectiveness of mathematics. I think it's a kind of an illusion, because I think what happens is that the pieces of natural science that we actually can do are the ones that we have tools to do. So there are many things about the natural world about which we have very little to say. When you look at the randomness of a turbulent fluid, when you look at the organization of a biological system, things like this, we don't have much theoretical that we can say about these things. We have a bit. I've worked on both of those things. So there's some things you can say, but it is something for which the traditional methods, mathematical methods, have not had much to say. And those haven't been things that have gotten sort of ingested in mathematical science and have turned into things where we've built engineering systems on the basis of them and so on. So it's a little bit of a kind of self-fulfilling prophecy that math will be unreasonably effective in the natural sciences because the things that we pull out to sort of consider to do in natural science are exactly the things that we that are things where we sort of know how to deal with them. They're things where we kind of have that way of thinking about it, and so that's what we pull out. Now, in what I think is true about sort of fundamental physics, it actually goes much deeper than that. There's this concept I call the Ruyad, which is this entangled limit of all possible computations, all possible computational processes. And my claim is that the laws of physics, as we perceive them, are the ones that observers like us sample from this Rulliad. So in other words, there are all these different possible sort of behaviors that are occurring, but the ones that observers like us, who have the kind of computational boundedness we have, who have the kind of belief in their own persistence of experience that we have, observers like us necessarily will sample from the Rulliad attributes that correspond to the laws of physics we know. But if we were observers different from the way we are, we might sample different laws of physics. So in that sense, it's saying the laws of physics we get are laws of physics that are determined by the way we are as observers. And so that I'm saying that there's sort of a junior version of that is what's led mathematics to be so effective in the natural sciences, because basically we've only done natural science in places where we can use methods that we kind of already knew from mathematics. Now, having said that, it is interesting to see that occasionally there have been sort of developments in mathematics that really haven't successfully been applied in natural science. A very obvious one is transfinite numbers from the 1880s, from Georg Cantor and folks like that. The idea of transfinite numbers is you might just say, well, there's this one idea of infinity, but actually there's a lot of subtlety to the notion of infinity. You just count up the numbers, 1, 2, 3, 4, 5, ... Eventually, the number you get that's past all the numbers you counted to is usually called omega, lowercase omega, the first transfinite ordinal. But then once you've got omega, that's the number you get to that's after all the numbers you counted through, then you've got omega plus 1. If you've got, if you say 1 plus omega, that's actually the same as omega. But omega plus 1 is a number beyond the number that's the one you got that was beyond what you got to by counting. You've got omega plus 1, you've got omega plus omega, you've got omega squared, you've got omega to the omega, you've got omega to the omega to the omega, omega times. That leads you to another number called epsilon 0. And you ascend in this hierarchy of infinities. Okay, so transfinite numbers, those are the simplest case of them is these transfinite ordinals. Those have never really found a use in natural science yet. I've had a number of cases where I've sort of come a little bit face to face with transfinite ordinals. And actually, there's a thing I'm working on right now that may bring transfinite ordinals into the story of renormalization and the infinities that occur in quantum field theory. But that's still future science. As it has been for the last 100 and something years, transfinite numbers haven't really made it into natural science. So that's an example of something which got built out in mathematics, but didn't make it into science. Now, in mathematics, there's a lot of different sort of possible mathematics you can build. You can just write down an axiom system and say, this is a field of mathematics I want to have. Some axiom systems will be kind of rather barren and uninteresting, but there are plenty of rich axiom systems. And the question of which ones we have bothered to study is partly a matter of aesthetics and partly a matter of ones where they seem to resonate with things we see in the natural world and which our senses kind of have us think about. You know, I think that so I mean, this question of we can invent lots of mathematics that will not sort of be something that relates to sort of sensory input that we have about the way the world works. In some sense, the Rulliad contains all of these possible mathematics. It is just that observers like us don't get to sample those and don't get to say that the physical world as we perceive it corresponds to something that is represented by that particular kind of mathematics. I think, well, a few thoughts on sort of the relationship between mathematics and physics. You know, there have been a number of success stories. Eugene Bigden was involved in one particular one in group theory, where group theory had sort of been invented originally in the 1830s, and then in the form of Lie groups, continuous groups in the 1890s, maybe. And Lie groups in their continuous form, Lie groups, the continuous groups, were really invented as a way to sort of clean up the mathematics of things like rotations. What does it mean to have two rotations? How do you combine rotations? How do you make infinitesimal generators of rotations? Things like this, and to generalize that idea. And then it turned out that the theory of all of that became extremely relevant when one was doing things like atomic physics and later particle physics, because the way quantum mechanics works, it kind of samples different, in effect, sort of collections of rotations and things. And that, so you really kind of need to know this group theory and the theory of group representations to be able to understand what happens in quantum mechanics. And that was sort of a piece of mathematics that was kind of ready and waiting when that was needed in atomic physics and so on. But it was a little bit, already inspired by something in physics, even when it was first built. But that was a place where kind of it looked like a kind of, the mathematics was there and waiting. I mean, in other cases, like in calculus, for example, I mean, calculus was originally invented by Isaac Newton, and his invention of it in the 1680s was really for studying celestial mechanics, studying orbits, studying the results of gravity and so on. Leibniz, who also invented calculus about the same time, had a little bit less a story of that kind of physics, more a story of things that were a little bit more sort of down to earth, of working out the areas of figures and things like this. So, a little bit less induced by physics there. It has been an interesting thing since the 1980s that there's been sort of an increasing realization that theoretical physics is a good driver for pure mathematical development. I think that's partly sociological and partly intellectual. The sociological part is physicists. Physicists just bash through things and get to answers. Mathematicians are usually like, wait a minute, let's dot the I, let's cross the T, do we really understand this definition? Let's be more careful. And sometimes it really helps to have the folks kind of hacking through the jungle, physicists, just getting to answers to give kind of a pattern of how you think about something. And then the mathematicians can come through and actually check that it was rigorous and really sort of figure it out. And that happened, for example, even with calculus. The calculus wasn't a very rigorous business until the late 1800s, really, or even the early part of the 20th century. There was a lot of kind of, oh, you can take the limit of this and it's probably going to work out okay. And that led to all these sort of pathological functions that became things like fractals and so on, where you say, oh, I've got a curve. It's not like the curve just jumps up discontinuously. The curve has an infinite number of discontinuities, and you've got to deal with that and things like this. And I think that there are plenty of places where physics has sort of said things that are kind of a mathematical consequence, but it really hasn't been able to nail it down mathematically. Another sort of famous one is the derivation of the behavior of fluids from the behavior of the molecules that make them up, going from molecular dynamics and taking the limit of a very large number of molecules and seeing how that limits to a continuous fluid. That was something people sort of wondered about from, well, the mid-1800s. People started thinking about that. David Hilbert, well-known mathematician around the turn of the 20th century, was spent years working on this limit of molecular dynamics. He never managed to figure it out. And people sort of said, well, it's probably kind of okay. We know fluids exist, and so we kind of think this limit must work somehow. We still don't know how that limit works. I made some progress on it in some things I did in the second law of thermodynamics. And I think some of the things that I've done make it clear why figuring out that limit is hard. It's deeply entangled with computational reducibility and so on. But it is notable that limit, we really don't know mathematically at an I's dotted T's crossed level how that limit really works. Actually, I care a lot about that limit in modern times because the theory we have of fundamental physics, starting from hypergraphs and so on and getting to continuum space, has another set of limits just like those, except they're even much more extreme than the ones that show up in molecular dynamics. And the question is, the things we're trying to do, And we're trying to build sort of a new kind of mathematics that can deal with these structures, spaces made from hypergraphs and so on. We're calling it infrageometry, geometry that starts from this underlying discrete structure and so on. But it is a little bit sobering to think that possibly our infrageometry, we may be able to bash through it, and we already have done that to some large extent at the physics level, but to sort of dot the I's and cross the T's, we're at 100 years and counting for more than 100 years for the molecular dynamics case. And I think it's going to, dotting the I's and crossing the T's for infrageometry is going to be a long issue that's going to have many tens of thousands of mathematician years that have to be expended on it. So a few thoughts on that. Let's see. Well, there's a question here from Des. What are some fields actually in imminent danger of being replaced by LLMs? Interesting question. I mean, I think if we generalize that to machine learning in general, there are some sort of image identification fields. I think radiology, pathology, these are two areas where there are pretty good results from machine learning. And, it's not a question of really replaced. It's a question of, look, you can get the machine learning to do that basic identification of things in the X-ray or the MRI or whatever else. And now, once it's flagged, this is a weird thing, then the humans can spend their time trying to figure out things that are beyond what you can just train an LLM to do. So I kind of feel like in a lot of cases, it's kind of floating things up to a higher level. I think that a lot of places where there's a lot of places where LLMs can help. It's not, they I think, largely just raise the bar for what the humans could do. I mean, there are a lot of places that I suppose one could slightly cynically call the justification economy of people sort of writing reports to argue why something is okay or whatever else, or various regulatory compliance kinds of things, where sort of the main thing is just produce an essay that sort of explicates this thing about why this building site is okay, or why this particular filing for something is okay, or this particular assessment of something is okay, or whatever it is. I think that it might seem kind of silly that to say, well, we'll just get an LLM to write all that stuff. But the fact is that what's happening there is one's using English or natural language as the interface between the person who knows the facts that they're trying to communicate and the person who's trying to extract certain kinds of things from those facts. So it's kind of like the LLM takes the bullet list of things that are true about your company, situation, whatever else it is. It turns those into this great big essay. And then the thing that's trying to figure out, are you eligible for this? Or did you do the right thing for that? Can then do its kind of slice and take this whole set of things you produced and then figure out from that, does it meet the criterion it's trying to look for, et cetera. And I don't think it sounds kind of silly. It's kind of like AI is talking to AIs. I don't think it is that silly. I think it's just that the interface language is natural language, and that's the way that we get to use those interfaces. But, I think there are lots of places that involve kind of interfacing two things, using the linguistic interface capabilities of LLMs, things like customer service, things like medical history taking. I think is another place where you can have a very patient discussion for an hour and sort of try and explore various different things with someone, and then try and summarize that here are some things that are flagged as being interesting. I mean, there are plenty of use cases where we can see LLMs being used as sort of an adjunct to something else. I mean, even in kind of, people have tried using them, I don't know how successfully, for sort of market studies and polling and things like this, where it's like you get those LLMs to have the characteristics of different kinds of customers, you prompt them that way, and then you sort of feed a question into that whole population of LLMs, see what happens. So, people, I tend to think that the story of job X is going to go extinct is kind of a wrong story. I mean, there'll be things, I mean, back in the day, there were people who were doing lots of calculations by hand and then, well, first computers and calculators, and then things like technology I built for doing mathematical computation came along, and those sort of extensive hand calculations became things that no human needed to do. Interestingly enough, at least a decent fraction. I mean, I watched this transition back in 1988 when we brought out Mathematica. There were people who were sort of proud of their ability to, I don't know, do integrals or algebra or whatever else it is. And some fraction of those people maybe felt like they'd been upstaged, but some fraction of those people were like, great, now I can just take that as being done automatically, and I can go and use my skills to sort of get to the next level. And I think that second thing is much more what one is liable to see. I mean, there will be people who will be left behind and who will say, who'll resist to the end, I don't want the LLM to do this or that thing. I think, but in terms of sort of a slam dunk, this has been replaced by an LLM, I keep on seeing places where LLMs are useful, but not replacements. I mean, another place where people talk about this a lot is in programming. To me personally, that's always seemed rather absurd because, what I've just been doing for the last 40 years is trying to build a computational language that automates a lot of the things that has as its built-in functions, the sort of primitive things you want to do. Low-level languages haven't done that. So in a low-level language, and something like Python or something, you're writing a big blob of code to do this thing that's one function in Wolfram language. And yes, the LLM can trot out the big blob of code, and maybe it can find these libraries to fill in, little pieces to what's needed in that blob of code. But to me, it's always seemed like, why are you doing this? We've already got that automation. You don't need to have the AI layer in there. Now, if you use the AI layer with Wolfram language, you can go even further, because then you can kind of take sort of the vague thing you're talking about, have the LLM help you crispen that up into this computational language, read what the computational language says, and go further. But the idea that programmers will be put out of business by LLMs writing blobs of code for them, those programmers, in a sense, shouldn't exist even right now. The fact that they do is sort of an anomaly of the way that the profession of software engineering has developed. And I think it's a weird thing because our tools let you, and this happens in many organizations and many people make use of this fact, with Wolfram language, you can do that thing that in sort of traditional programming might take you a month, you can do it in a couple of hours. And the thing that's happened, the thing that I see increasingly, is there's a certain type of person, like myself, for example, who just wants to get the job done, and then they know there's another thing to do, and they've figured out, what I like to spend my time doing is figuring out what I should do next, not in the actual mechanics of doing those things. So for me, if I have an environment, which I do, where I can be super efficient at taking an idea and turning it into a real piece of computational language that my computer can run, then that for me is a big win. If I was sort of a software engineer by profession, then that isn't really what I'm set up to do. What I'm set up to do there is just implement things. And it's a different workflow. And when that's what you're doing, when you get to the point where it's like, well, what should I implement next? It's like, oh my gosh, I wasn't set up to think about that. That's not what I was sort of trained to do. And it all seems very difficult. It's much easier for me to do those mechanical things. And yeah, well, it's easier for you to do those mechanical things. It's also easier to automate those mechanical things. And again, we've sort of already pre-automated many of those mechanical things, and LLMs provide kind of a in some cases provide just something, well, we already did that. In other cases, they provide things that aren't sort of in the direction of the kinds of things we've built a computational language to do, just because they're things that relate to operating systems and user interfaces in ways that aren't really what we've been dealing with, which is really computation for the sake of computation, rather than computation for the sake of kind of managing the operation of a computer and things like this. So, I feel like that's a place where there's more automation coming there, which will force people to be more in the mode of what they have been doing if they've been using Wolfram language for the last however many decades, of the main thing that's of human importance is figuring out what you're trying to do next, doing the computational thinking to work out sort of how to think about the next thing. And I think that's the thing that's kind of that's so yes, maybe that'll sort of force more of that realization of automation in a case like that. But I somehow there's nothing really that seems to me to be a thing where it's a kind of slam dunk. The LLMs can do it now. We just don't need people to do that at all. There's sort of definitely there are lots and lots of places where LLMs can help, and whether people choose to sort of be lifted up by that and do more, that's an interesting thing, somewhat societally determined, somewhat determined by the traditions of different fields and so on. But a very large number of fields have sort of places where they can be helped by LLMs. Let's see. No good comments. Deep learning is apparently automating learning in general. I think if your job is learnable, then deep learning will be able to automate it. I don't know. I mean, there's an awful lot of jobs that you could say are learnable, but up to a point. I mean, it's kind of, you can learn to be ready to think about the next creative thing, so to speak, the next thing that is a human choice about what to do. And you can learn how to be more effective at doing that, running a company or something. You can learn how to be more effective at making decisions to do that. But there are many decisions that could be made, and it is ultimately going to be some human choice which of those decisions you want to make. And I don't think that is something that you can expect to automate. There are many lower level kinds of things which, yes, that they're more amenable to that. Let's see. LC comments, it seems inevitable that mathematics gets entirely subsumed under CS in the sense of symbolic representations in their processing. I don't think that's really true, actually. I think that mathematics, as pure mathematicians do it, has a different arc of purpose than computer science has. I mean, pure mathematics is really a story of kind of the aesthetic and intuitive structure of mathematical things. It's like, what can we imagine? What can we build? What kind of new form of geometry can we construct? How can we fit together these ideas and so on? And yes, there's mechanics underneath there of this thing that we aesthetically constructed. How do we prove it, in this, this step, this step, this step? And some of that seems a bit mechanizable. I mean, much of that, my own efforts, our own efforts, have taken a lot of the sort of calculational parts of that and really sort of compressed that out. And there are a few more pieces that are kind of the mechanical proving steps there that you can sometimes maybe automate out. Although most of the time, most of the proving effort is to explicate kind of the intuitive structures that are being built into pure mathematics, rather than just mechanically to grind through and figure out this is a true result, this one isn't. So I think when it comes to computer science has sort of a theoretical branch that's a bit more like mathematics and that has proofs and things in it. But I think that the sort of the structure of what you're trying to do. I mean, okay, so a thing about mathematics. I think most mathematicians would say mathematics is about, pure mathematicians would say it's about creating structures, proving things, understanding how those structures work through the proofs, things like this. That's very different from what, for example, Wolfram language is all about, which is just compute the answer. Just get to the answer. I don't care, by all means necessary, get to the answer. Whereas mathematics is much more about, let's understand the structure of how we got there, so to speak, and the structure of the things we were building in getting there. So it's really a different kind of activity. And in fact, those two activities are surprisingly, I think that mathematics, pure mathematics is a deeply human activity in many ways, because it's all about developing that intuition, creating these structures that we humans can understand. And it's not really so much about, except as a tool for doing that, just get to the answer by all means necessary. Let's see. Quantum comments. Plumbers and electricians and hands-on people are safe for the next few years. Researchers are the ones who might get replaced. If a researcher is getting replaced, it just means they're not a very good researcher, I think. Because, these things where you're figuring stuff out, if you've got a tool to let you figure out more, then you'll be able to go further. I mean, it's like people, you could say that when, Mathematica came out and so on, that could have replaced researchers in areas of the mathematical sciences. And in a few tiny cases, maybe it did, but mostly it just let researchers do more. It took one of the things that they wasted a bunch of time doing and zeroed it out. It's kind of like, there might be a thing where we could have spent a lot of time back in the day, before my time at least, making quill pens out of feathers. Before we could ever start to write our great research paper, we would have to, use a knife to sharpen our quill pen. Well, turns out by the time I was around, at least, when I was a kid, you didn't have to do that. I mean, I still used an ink pen where you still had to fill it up from a glass container of ink or whatever, and it could get very messy and so on. But pretty soon there were ballpoint pens all the way down, so to speak, and that became irrelevant. And so that made it possible to be a bit more efficient. And that's true with many kinds of tools. It's just like it raises the level of what you can do. Now, when it comes to manual skills, it's absolutely true. We don't have automation in that area. The fact is the intellectual skills had a step forward before the manual skills had a step forward. I think I've probably talked about this before, but my strong guess is that it won't be long before there'll be sort of a ChatGPT moment for basically humanoid robotics. I mean, us humans have, I don't know, 200-300 degrees of freedom. There are now routinely robots with 60 degrees of freedom. There'll be robots that can sort of articulate as well as we can, that have little actuators. We still are winning the sensors thing. We have millions of sensors on our skin and so on. Robots have fewer so far, but they'll have more. And they'll probably have general purpose ones, just like we and robots can have eyes, where you have a very large number of pixels, millions of pixels, in a single image. That isn't yet a thing for touch, but that's a reasonable possibility to imagine kind of a material that can be used as a, skin of the robot, and wherever you touch it, it can know where you touched it, and you have kind of a thing that's a little bit like the image case, but for touch and so on. And there's, various kinds of proprioception sensors of how much did this joint move and things like this. But so there's a certain amount of sensor data that still has to develop, but it's getting there. And then it's a question, well, can you sort of make the robot do these sort of actions that are like what humans do, like what construction workers do, plumbers do, whatever electricians do, those kinds of things. And the answer, I suspect, is that a bunch of that kind of, one could say last mile, but it's not really last mile at all. It's last few inches or whatever of just go do that thing will probably get automated. Even, it'll be like go, take this stake and, bash it into the ground. This location, go do it. And the robot will go do it. Or go take this, install this window in this location in this house and, attach it in this way and so on. A robot will be able to do that. And I think it's kind of like, it's like you've got this sort of robot that can go and do the end part of what needs to be done. And so, yes, those professions will also, I suspect, get sort of a boost of efficiency, possibly, in the amount that can be achieved by a person. It's like, okay, the plumber shows up and there's a bunch of things to do, and the plumber can deploy 5 robots to do those things. And the plumber is making certain judgment calls about what should be done, but it's kind of it's like there are many plumbers' mates, so to speak, that are going and doing the detailed work, but now they're robots, so to speak. So I kind of tend to think that will happen, and it might happen quite suddenly. I think the hardware of humanoid robots is really getting to the point where if the brain could be able to do these kinds of human-like actions, that it could happen quite fast, and that will be another kind of sort of shock to the world. I think that as we look at these different attributes that we humans have, yes, we've been gradually automating more and more of these attributes, and the thing that sort of the human choices we make are the things that, in a sense, are the things that sort of feel unique to us. And yes, it could have been the case before GPS. It's like, I feel very human making the choice to go on this road rather than that road. And now all the fun's been spoiled because I just follow my GPS. I don't hear too many people saying that. And I think what will happen is sort of the value of human judgment will go up. The value of kind of the mechanics of doing things will probably go down. Let's see. LC comments. What do you think of David Deutsch's view that knowledge and progress is essentially unbounded, i.e. there's always more to be had, and lack of knowledge is at the bottom of any and all issues? Well, first point is there always more to discover? The answer is definitively yes. Provably yes. That's not even a we have to have opinions about it. It's, if we think about sort of computational processes and computational irreducibility and so on, there is always more to discover. There is an unbounded collection of things to discover. That's a consequence. We can trace it back to things like Gödel's theorem, ideas about computational universality and so on. But I think it crispens up in computational irreducibility, but there's always more to discover. There's always more that you can discover about sort of how to make things in the world as well, inventions to make. There's always more things where you take the raw material of the world and figure out how to get this or that thing to happen in a more efficient way, given what is there in the world. I kind of think that fact that it's possible to always have more inventions is kind of why one has the impression in economics that the aggregate value of the world is continuously increasing, which seems kind of like, how can that be right? Why isn't it kind of a zero-sum game to, somebody wins, somebody loses in the kind of economic system, in a closed system? I don't think it is that way, because I think one's always mining more kind of computational reducibility out of the computational irreducibility of the world. One's always discovering these little pieces, these little pockets of reducibility, these little ways one can jump ahead. And I think that's related. I don't know for sure. Something I'm planning to think about. I think that's related to kind of the creation of economic value and its progressive creation in the world. And that process of there's always more to invent, there's always more to discover, never going to run out. You're never going to run out of mathematical theorems. They're an infinite number. You can study as far as you want. You're never going to run out of technological devices you could invent that will make something more efficient and so on. Now, the question is, are we going to run out of things we care about inventing? Is it going to be the case that we say, well, for our lifestyle, we know everything we need to know. We don't need to know anything more in our particular lifestyle. I'm reminded a silly story I just reminded of. Years ago, I was at some dinner at some college in Oxford, actually. And there was a crusty old chap who was I don't know, ancient historian or some such other thing, who somehow we were talking about the modern world. And he was like, this was in the after dinner phase where everybody was passing around, port, which I don't drink. I'm not never developed the taste for alcohol, so I'm not a port drinker. But in any case, that was a sort of a social moment in the old world, I suppose. And this chap was opining, I think, somewhat to be provocative, that the only thing he thought that was really for him a useful consequence of modernity was the Teflon kind of under thing for this port decanter that could now be passed around the table more efficiently. I think that was maybe said as a kind of piece of provocation more than a reality. But you can imagine that you can have a rhythm of life where the additional inventions of modernity don't really matter. And in some cases, you actively, say, I don't want that stuff. I'm really happy the way I am. So it can be the case that one can get to a point where people are like, I'm happy the way I am. Now, the world and nature probably throws curveballs at one from time to time, because there's sort of the whole computational reducibility story says there'll be things that happen in nature that we couldn't readily predict, and that will be different from what we've seen before. Whether that's, the climate is changing, or the asteroid is arriving, or once this has been developed in this way, it's inevitable that the species will do this and this and this. So, nature throws us, I think, inevitably a certain set of curveballs. Probably the very development of society does that. There's probably computational irreducibility in the way that society develops to the point where we have to, where we're sort of forced to confront new things. And so we can't kind of rest on our laurels and just say, we've learned enough. We don't have to figure out anything new. There's nothing more we need to discover. There's nothing more we need to invent. But so my guess is that there'll be a driver. There'll be always a driver of new things that have to be invented. I mean, we know from the arc of history that there are certain cases where civilizations have got to the point where they were just sort of not inventing things, and then somebody else showed up and they had invented, guns or whatever it was, and or stirrups or whatever the story was, and it's sort of bad news for the folks on the other side, so to speak. So, and that can happen with respect to nature as well, that's. But I think so. I think we're not going to run out of things to invent and discover. We might run out of motivation to need to look at them. To the claim that lack of knowledge is the root of all issues, I don't know if I necessarily agree with that. I think that there's actually, I would even argue that the belief in knowledge can sometimes be more dangerous than the lack of it, so to speak. In other words, when you believe, oh, I'm very scientific, I've learned all this science, I know all this fancy stuff, and therefore I know everything about what's going to happen in this case or whatever else, that leads to more sort of bad decisions than saying, well, I don't really know enough about this, and so I have to use kind of general judgment about this thing, rather than I've scientifically proved that nothing can go wrong, one might say, even though, to common sense, it would be like, wait a minute, is this really going to work? But, if one thinks one has the knowledge that one scientifically proved it, that's the place where you really run into terrible trouble. So I think it's it's a complicated thing. And there's a certain belief that has tended to develop that kind of, if you have learned all this technical stuff, that means that you can figure out all these things. And sometimes people tend to switch off their kind of common sense judgment because they say, I know this whole tower of technical stuff. Oh, that's what I need to know, even though the sort of giant freight train is bearing down on them that would be obvious from common sense. But they don't sort of get to that because they're thinking only about their technical tower of knowledge. Let's see. LC comments on a future job title, miner of computational reducibility pockets. Yes, I think that's a pretty broad job title, actually. I think computational miner in general, somebody who goes in and tries to mine useful stuff out of the computational universe. I've done a fair amount of that. It's not yet a job title. I just invented a bunch of new job titles at our company, so that one hasn't yet come up, but it might do before too very long. Gabe asks, what is your take on AI-based research developed for sifting through space for the hunt for Earth-like planets? Well, it's very popular these days to say we're using AI for this or that. Just like people say, I've been working on AI for decades. And what do they actually mean? Often what they mean is they're using statistics, which is, yes, a couple of 100 years old. And many of the methods are that old. And, there are sort of upticks to that usually involve computers in more serious ways. And, I think one has to, the fact that we are making more serious use of computers to do this or that thing, that is clearly a win. To say, we're just going to ask an LLM, find more exoplanets for me. It's like, I'm not really believing in that. I do think that there are places where there may be things that are sort of in the literature of some particular field, even astronomy, for example, where it's like there are effects where nobody has noticed that these 100 things that people have mentioned, oh, did you notice that this quasar had a lower intensity line of this kind, and this other one had this thing and that thing, and so on, that nobody had sort of put all these pieces together from existing experiments. That might be a thing that LLMs could find. But the notion of, go fetch exoplanet LLM, I'm a bit skeptical, although using computational methods and methods that even make use of the mathematics of machine learning to do that, perfectly fine idea. I would not expect magic. I would expect incremental progress. I think that, we've seen the same thing, a very popular target there is drug design, of being able to sort of figure out a molecule that has just the right shape to do this, just the right kind of thing. And so far, there are not, to my knowledge, any drugs that are actually in the approval pipeline that, well, at least in clinical trials, that are based on things that have been found by just tell the LLM to do it. Although it is clear that there's a lot of intuition and general utility that comes from being able to do machine learning based protein folding and things like this. But it's sometimes when people say we're having an AI look for new materials or some such other thing, when you peel back the covers, what you discover is they're just enumerating different cases with a computer. And yeah, there's a computer, but I wouldn't necessarily call that an instance of sort of true AI in the sense that it has emerged in the post-ChatGPT period of being sort of neural net based methodology. All right, I think I need to go back to my day job here, but thanks for lots of interesting questions as usual. And I look forward to chatting with you all another time. So thanks and bye for now.